available on my cloud. Some of them are not. Some of them I haven't downloaded yet. I had skimmed through my YouTube load, and it didn't look like they were being viewed, so I hadn't been really keeping up with the uploading from the Canvas cloud to the YouTube channel that I have set up. I will see what I can do about catching up on some of them. Some of them, I think like I said, I missed part of this lecture. I think there's another one that I missed part of. I will see what I can do about catching up, but I don't have all of it recorded. All of it is in the notes, okay? All of it is in the notes. All of it is in your textbook. I don't have all of it available as explanations. You can always send me email. It's like, I got to this part, have no idea how you did this next step. Just send me email and go, okay, I don't know how you got from here to here, and I can send you an explanation to go with it. Let me find the homework set so I can talk about that for a moment. It's somewhere, if I can figure out where I put it. Yeah, one of these days I'm actually going to get this all organized. Of course, by then we'll probably be done with the pandemic. We can always hope. Oh, that was not the right file. Homework. All right. So this is the homework set that's loaded. I went ahead and gave you the Ka for lactic acid. And my recommendation is that you approach this first problem. The first part you can do with the Henderson-Hasselbalch. The second part is a little bit less straightforward, but it still is tied together there. We've got another one here that is Henderson-Hasselbalch as far as the first part goes, but then you are going to have to do some calculations to figure out what happens after you add the hydrochloric acid. This is designed to mimic one of the examples that is in your chapter notes. Then I swapped over to some KSP stuff. And yeah, they're kind of, because this was at the bottom of the page, it looks like they're kind of squished together. I gave you a mythical compound. I didn't actually identify what it was for you because you don't really have to know that to solve the problem. I gave you a solubility. I gave you a molecular weight. Figure out what your KSP is. We've got KSP in pure water, meaning it has no common ion. But then I gave you a second part where it does have a common ion. You will not get the same solubility for A that you get for B. Or you shouldn't, but let's put it that way. For 5, this one also kind of mimics one of the examples that I gave you in that it asks you to show how your pH is going to affect your ability to create this precipitate, because you have calcium chloride and you are placing it in a solution that has a relatively acidic, actually, I read that wrong. Like I said, it's been a long day. I read the wrong number. Oh, okay, yeah. 0.5 is not acidic. Okay, 0.5 is actually the molarity concentration. Here's the pH. Okay, pH is 8. It's slightly basic. Okay, which will affect your solubility. And then there's a conceptual question predominantly on the KFs. And if you would like to attempt it, there is an extra credit question that involves the selective precipitation. Obviously, you don't have to do the extra credit one to turn in your homework set.
Should I have access to this homework yet? Because I don't see it up.
I thought I had loaded all the homework. Let me flip back to my other. No, I didn't. Let me see if I can do it now. I thought I guess I loaded all my notes and actually didn't get all my homework loaded. I have so many things going on. So add my item and then click on it. See if I can insert. I'm setting it for the standard online submission. And let's see, today is April Fool's Day. As I saw something online that said April Fools just should be sort of, outlawed until we get rid of the pandemic because everything's kind of a wreck. So let's see, today is the 1st. So homework will be due at midnight on the 6th. Because that way it will give you the entire weekend and until midnight that day. Hopefully, fingers crossed, it is successfully published now so that you can view it. Yeah, like I said, I thought I was pretty sure that I had loaded a bunch of stuff, but I'm thinking what I loaded to the pages. Because if I open my pages and it says notes by chapter, yeah, I did actually remember to load all the notes for the entire rest of the semester. I just hadn't loaded all the homework for the rest of the semester. So
it's there now.
Yeah, it hopefully should be viewable and all of that. All right, hopefully problem solved. All right, so we are done with buffers and KSPs. We're not entirely done with equilibrium. That never quite entirely goes away the rest of the semester until we actually talk about nuclear. I only want to cover just like a section out of the next chapter, which of course means I have to go hunt for my notes again. Thermochem notes. Okay, stop. I'm trying to share the wrong thing. Thermochem notes. Aha, finally in the right spot. All right. Thermochem is kind of interesting. Thermochem is something that we got introduced to in first semester. We even did a lab on it, the whole coffee cup calorimetry thing. We talked a little bit about delta H's in first semester. This kind of starts with a similar idea and kind of takes you down a different path. This is another chapter where there is some overlap between chemistry and physics as far as how you manipulate energy. So we kind of start here with the paraphrase. Okay, this is not the actual way that a first law of thermodynamics is written, but the best way to sort of understand it is energy can neither be created nor destroyed. Okay, but you can change it. Ought to maybe sort of be the addendum to that. We talk about the word spontaneous in chemistry and think about it in terms of what does this mean in terms of mixing things or having them happen on their own. Okay, so from a English point of view, spontaneous usually means something like able to do something at the drop of a hat. If you are spontaneous in your ability to pick up a musical instrument and play a tune, okay, you don't really have to think about it too hard. You can just like pull something out of your brain because you already know how to do it. Some people are sort of spontaneous in their desire to party. For chemistry / physics, it is something that occurs without outside intervention. Okay, you don't really need anything to make it go. At most, you might have to pour two things together. Okay. So if you had two beakers, one with an acid and one with a base, and you poured the two of them together, you're going to get an acid-base neutralization reaction to some degree. It may not be a complete reaction. You may have a certain amount of equilibrium involved, but you're going to get a certain amount of neutralization just because it happens. It is a spontaneous reaction. If we talk about it on a little bit more physics point of view, okay, you pour water, it runs downhill spontaneously. Unless you have a pump, it is not going to run uphill spontaneously. However, there is a communication, that's kind of the wrong word. A incorrect assumption is maybe more of a better description here. Spontaneous doesn't mean fast. Glaciers are spontaneous. They sit there and do their thing 1 inch per year over thousands of years. Nobody has to interfere. They just do it. Of course, these days, global warming is a factor, but on a geological scale, glacier movement is spontaneous. Definitely not fast. You do have to follow the laws of thermo, okay? Again, like I said, this is a chapter where there is a fairly hefty lap over between the things that govern chemistry and the things that govern physics in terms of how reactions and how mechanisms occur. So if I have, and I've moved my thing here so that I can't see my little arrow. There's my arrow. Okay. You need to kind of back up and start at the very, very beginning. And only physicists with their somewhat twisted version of how you ought to number things go, well, there has to be something before the first, so we're going to call it the zeroth. And the zeroth law has to do with a really weird, abstract way to talk about temperature. So we have seen in chemistry Fahrenheit and Celsius and Kelvin. If you take engineering classes, there's a couple of other versions that you may encounter. I think Rankins is a temperature unit that's used in a particular version of engineering. But you don't actually have to know what the number values are to actually understand what the temperature means. So look at the way it's worded. We have two systems that are in thermal equilibrium if they have the same temperature. Okay. If I take my can of Diet Coke that's on the countertop, because I never got around to putting it in the fridge, okay, and I pour it in a glass, okay, yeah, I transferred it to a different container, but the stuff that's in the glass is the same temperature as the stuff that was in the can. I don't actually have to know whether I'm in Fahrenheit, Celsius, or Kelvin. I can assume that they are the same temperature because there was no change, okay? There was no heat input and there was no heat given off. On the other hand, if I take my Coke out of the fridge and sit it on the countertop, over a period of time, the warmth from the air around the can and a little warmth from the base of the can where it's sitting on the countertop will eventually warm the can up to room temperature. But originally, they were not the same temperature. Okay. So again, you don't actually have to know the number values in order to determine that they were not at thermal equilibrium. Okay. It sounds really kind of oblique, like unobvious. There's a reason for doing it this way. It allows you to have situations where you may not need to know what the actual temperatures are in order to figure out which direction your heat is going. So if you take an ice cube and you drop it into your coffee. Okay, I am so guilty of this because otherwise I inevitably pour it out of the coffee pot, okay, because I think Keurigs are evil, and grab up my coffee cup and immediately burn my tongue. Okay, so over a long period of time, I have developed this really kind of habit of grab an ice cube out of my freezer and drop it in my coffee cup before I commence to drinking it. But we have no thermal equilibrium until the ice has melted. Because, okay, the ice is cold, the coffee was hot. I put them in combination with each other. Therefore, the heat from the coffee is flowing toward the coldness, okay, which is the ice cube, and give it a few minutes. There's no longer an ice cube in there, okay? It's now melted. I now actually have achieved thermal equilibrium. The liquid that was in the ice cube is now at thermal equilibrium with the liquid from the coffee. Okay. So this kind of brings us back to a more truthful, or maybe we should call it a more actual statement of the first law of thermo, which says the total energy of the universe is a constant. So a whole bunch of the things that we talk about in this chapter, I will steal a description from a science fiction author that I'm really fond of, who I think doesn't write much anymore, who's named Simon Hawke. He wrote a series of books called The Time Wars that I adore. But he coined a phrase known as Zen physics. The idea that a lot of high level physics, which kind of laps over into higher level chemistry, has a kind of almost philosophical component to it. So when you say the total energy of the universe is constant, that also imparts a whole bunch of other ideas, which we're not going to get too deep into, but all the energy that we have has existed since our universe began. So we'll dive for just a second into Big Bang theory. And the idea that the universe had a starting point. All of that energy continues to exist. Now, it may not be usable, okay? Think about the gasoline in your car. This is another thing that we'll kind of circle back around to. Yeah, our ever increasing expensive gasoline right at the moment, due to everything from the boat stuck in the canal to the ice storm that happened that affected the plants that do oil refinery in Texas, that got a lot of them got damaged during that ice storm a couple months ago. So all of those things, our gas prices are going up, which is kind of sad, but put gas in your car, drive your car. Obviously, it made your car go. It also heated up the engine due to frictional forces, increased the temperature of your tires slightly due to friction. The exhaust coming out the back end of your car is heat. All of that energy still exists. Can you gather it back up and use it again? No. It doesn't mean that it ceased to exist. Its usability has changed. That's a big component to this, of you can change energy from potential to kinetic or back, but you always lose something, okay? There are no such things as perpetual motion machines. You can't have a perfect scenario where you never lose your usable energy. Okay. If I have one of those little drinking birds that like nods forward and, looks like it's going to dip its face into a glass. Okay. And you give it a little plink with your finger and it starts rocking back and forth, and it'll go for quite a while. But there's a little bit of friction in the hinge joint where the bar is, where, the bottom part is connected to the top part. There's also a little bit of air resistance. So all of those things slowly over time diminish your usable energy or useful energy. So the last thing we're looking at here tonight is, let's look at a combustion reaction. So methane something from very beginning of the semester. Methane burns. Methane is natural gas. Methane is what powers our Bunsen burners in lab. It burns very decently in the presence of oxygen. You get two main products. You get carbon dioxide and water, but you also get heat. Back in the first semester, we measured heat values in terms of enthalpy, ENTHALPY, and gave it a symbol of delta H. So the little triangle, delta, and H, and the little degree symbol just means it's been standardized. So this is an exothermic reaction. Think about it. You light your Bunsen burner for lab, it provides heat, okay? It's exothermic. It's also spontaneous, okay? If you did not provide the spark to light your Bunsen burner and you just had a sample of methane and you left it in the presence of oxygen, it would eventually react. Now, in that particular case, it reacts much more slowly. Because remember, speed and spontaneity are not identical. Okay, you could be spontaneous and really slow. Once you provide that spark, then you get the heat and all being produced relatively fast. But it would actually react on its own. Okay, so we're going to pick up next week talking about entropy, which is yet another thermodynamic idea that involves randomness or disorder. And I would say my house is the prototype for entropy right at the moment, especially considering that I have no staircase and all of the things that were in the closet underneath that staircase are now in boxes piled all over the house, as well as all of the food that was in the cupboard that we refer to in my house as the pantry is now also in boxes all over my house. So I have a lot of entropy going on at home right at the moment. So we will continue onward with thermodynamics next week. Keep in mind, okay, do your homework set over the weekend so that you can turn it in on Tuesday night. And we are heading toward the next test, test number 3, which is a mixture of acid-base equilibrium, KSPs, and buffers. So that will be probably coming up. Okay, obviously not this weekend. It will probably be next weekend, because if homework is due on Tuesday night, and fingers crossed, I grade it on Wednesday or Thursday morning, and we go over it on Thursday night, that will then give you the standard thing that I've kind of been doing this semester of giving you the from Thursday at midnight all the way through till Monday at midnight to do the test. Questions? We are drawing closer to the end of the semester. We have almost exactly a month left. Final exam, I believe, is on the 6th. Let me look at my Google calendar thing. Yes, that should make the final exam be on the 6th of May. All homework has to be turned in the previous day, the 5th. Lab is a couple of days back because since it takes a long time to grade stuff online, Keep in mind, since the majority of you I have for lab, keep in mind that all of your lab stuff is due Monday, May the 3rd. Okay, so it's kind of, I tried to line it up so not everything is absolutely due on exactly the same day, but it also means lots of people need to finish up their lab stuff so you can get it to me. People are catching up. Okay, it's getting a little bit better. But I still have a lot of outstanding work, and we still have, let's see, some people have 2 more labs to go because I only saw yeah, you can turn in late homework up through midnight on the 5th. I just need a day to grade homework before I have to grade exams and finish out final grades. Because if I give, okay, the way it works for the system, this is from the professor end of things, is if I give the final exam on the 6th, which is a Thursday, I have basically until Friday evening, 24 hours to submit grades. So yeah, homework should be turned in before is good, okay, but homework needs to be turned in by the day before the final exam, which is the 5th. Late homework is okay, you lose a few points, but late homework is better than no homework. Other questions? Otherwise, hopefully they will fix my staircase and I will actually have stairs by the end of the weekend. Otherwise, I will see you on Tuesday.